we now look at inductors in AC circuits, and let's see what happens here. So if I have an inductor like a solenoid connected to my source, okay, so once again my source is V naught sine omega t, and the potential across the inductor must instantaneously match the potential from the source again, since Kirchhoff's loop rule has to be satisfied. Okay. But the self-induced EMF across an inductor, remember, is equal to negative L di dt, but that's the induced. Okay? So the voltage from the source must be in the opposite direction of this negative sign. So my source, the induced is still negative, but my source, the voltage from my source, must be equal to L di dt. Okay? And this is because your source is going to be in the opposite direction of your induced, which must be the case because the induced is your back EMF. Okay? So with that in mind, we can now say that V naught sine omega t is equal to L di dt. And if we look here, what we will see is that di dt is equal to V naught over L sine omega t. Okay? And as a result, the current, if I solve for the current here, okay, I'll take this integral and I'll go from 0 to some generic time. So I'll slap primes on the integration variables here. And V over L, V naught over L is constant. The integral of sine is minus cosine. Oop, I don't need the dt anymore. And I'm going to need to divide by an omega. Right? And once again, cosine and sine are shifted by 50 or 90 degrees, pi over 2. And so now once again, we can look at this equation. Now we still have this minus sign, but I can look at this equation and I want to compare this to Ohm's law. Now, before we do that explicitly, let's kind of go back and review if I plot the voltage of my source over one period, then my current here starts with a negative cosine. Okay? So, what happens here is that your current um, is going to lag behind your voltage, right, of your source. Okay? Your current is going to lag behind your voltage by 90 degrees. So, your voltage starts at 0, and then 90 degrees later, your current is at 0 and then in the same direction as your voltage was at that time, or at time equals 0. Okay. Um, and as a result, what we will do now is going back here to these two equations. If we compare, we can see that R is equal to L omega. So what we say, we call this the capacitive, or not the capacitive, but the inductive reactance. Okay, your inductive reactance. And what this means is that Henry's times our angular frequency is equal to ohms. Okay, so this acts like a resistor, or I should say this is how an inductor acts like a resistor for AC circuits. Okay. And so once again, we can look at the two extreme cases. And that is when omega is much, 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 much larger than 1. And when omega is much smaller than 1. Okay? So, if we look at this case, omega being much, much larger than 1, this is very high. And if you think about it, this should make some sense, because for a inductor, okay, your back EMF is equal to negative L di dt, right? And so if this is a very rapidly oscillating source, then di dt is very large. And what that means is your back EMF is very large. So the induced voltage from the inductor is going to fight the current trying to be pushed by the source. And so then this just acts like a very, very large resistor. Okay? So it should make some sense that if this is very high, this reactance is very high. If omega is very high, the reactance is very high. But if omega is very small, then, okay, so let's label this case 1. If this is case 2, then if this is a very, very slowly varying current, or I really should say voltage source, if this is a very, very low omega, then that means that my voltage is very slowly varying, right? Whereas up here, my voltage would have been, once again, and even though my current is offset from that, by a cosine that would look something like this, if I look at this current right here, if omega is small enough, then over some finite interval, this is approximately constant. And that means di dt is approximately 0, which induces no back EMF. And if there's no back EMF, then there's nothing to fight the current. So when you have very low omegas, your reactance from your inductor is also very low. And it acts like an open circuit. By the way, the term for the very high, where the circuit basically shuts down, this is a short circuit. Okay. So at very high frequencies, your inductor acts like a very, very strong resistor. And at very, very low frequencies, it acts like a very, very small resistor. Okay. So if you can adjust your omega small enough, then it would almost be like your inductive reactance is pretty much 0. And there is no back EMF then being generated by the inductor because di dt equals 0, and therefore nothing to impede your current. So your inductors and your capacitors both behave very peculiarly in these AC circuits, right? And so then in the next video, we'll talk about what happens with all three capacitors, inductors, and resistors. But once again, to kind of think about this phasor diagram, and by the way, something I didn't mention in the last video, the phasors here are going to rotate with the through an angle equal to omega t. Okay. So what we mean by that is, let's first draw these things. So the potential, or I'm sorry, the current through the circuit let me make sure I get this right. Yeah, your potential across your inductor is going to lead your current by 90 degrees, right? So in the capacitor case, your current led the voltage, and in the inductor case, the voltage leads the current. And so then this is going to rotate until when you go through one complete cycle, you'll reach back at this point, right? At this configuration. But your two voltage and current vectors are going to rotate, and the angle that they rotate through is going to be equal to omega t. So at any time, you can calculate where V naught and I are in this, what we call the phasor plane, um, if you know what omega is, because then you can just multiply omega times t, and that's the angle that these phasors would have rotated through. Okay, so in the next video, we'll combine all three elements, resistors, capacitors, and inductors in series, and see how their phasors work, and see how the total quote unquote resistance acts in the circuit. We'll introduce a new term for that. Of course, we don't call it resistance, we will call it impedance. But we will explain how that works as well. So here are inductors in AC circuits.